Okay, the last part we were looking at dealt with very quantitative work. That is, given data that is assumed to be linear, predict what happens elsewhere along the line. Okay, that's an important thing to do, but there's also something very different that I think is going to be very important for just mathematical fluency, is doing something that's not as quantitative, doing something that's more qualitative, really. And this is still very important, but it's a really completely different idea, is that let's say you're given a graph where the x-axis represents something, like some quantity, represents some number, some real-life thing, and the y-axis represents some other quantity. Then interpret what happens with one quantity as the other quantity grows or shrinks. So typically, you end up growing or shrinking the x-coordinate, and then talk about what happens with the y-coordinate. And graphs, just to clear up how different this is from the last part we were just looking at. Now, graphs made from real data might be linear or nearly linear, and maybe that can happen because maybe, depending on what you're looking at, a linear model might be the right model. That might be right. Now, probably nothing in real life is perfectly linear, but it might be a decent model, might be a good approximation. But graphs made from real data might not be linear at all. It's just because maybe a linear model might not be the right model for that particular application. It is what it is, right? So sometimes the graphs you look at are very line-like, almost very straight, and other times they're not. But shouldn't matter. No matter what, in all cases, just read from a graph the data, read the real data that you get based on the graph that's presented. So based on the graph below, describe what happens with the number of coronavirus cases over time. So there's a time axis here. We can see based on like a labeling of January, February, March, April, May. And then you can see number of cases along the y-axis. So I assume this means like 1 million, 2 million, 3 million, right? And so to try to address what's going on as you move forward in time. So as you move from January and then you think about running the video in your head as you increase and move towards the future from January. So as the months progress, you see the y-coordinate. So as the x-coordinate grows, you see the y-coordinate grows. And the y-coordinate grows it's about the number of confirmed cases, right? So to put this completely in words, we don't really want to talk about x-coordinate grows or y-coordinate grows. We want to talk about and put this in the language of the specific problem. So as the months progress, the number of COVID-19 cases in the US is increasing. Or to try to clarify, that is, in later months, there are more total confirmed cases. Let's try another one. Based on the graph below, describe what happens with the popularity of cigarette smoking among youth as time moves forward. So youth, teen, I hope that's okay to use as synonymous here. So as we move from the past into the future, so from way back when, as we move closer to today, so from 1997 all the way up to 2018, at least that's what this graph is showing, the popularity of teen cigarette smoking is waning. So you see cigarette smoke is shown in this. There's actually two graphs here, right? But the blue graph, the y-coordinate, shrinking, going from like 36% down to 30%, down to 20% right around the year 2009. So over time, teen cigarette smoking, according to this graph, is getting less popular. I guess this is from the New England Journal of Medicine. But just because it's here, because there's a second graph on vaping, just wanted to mention that at first, there's an initial level of popularity of vaping for teens, and then it actually, according to this graph, seems to be getting less popular. It's not as fashionable for teens. And then after hitting some bottom point here, like around what I would guess this is 2016 or 2017, somewhere in here, then it looks like let's see. It looks like teen vaping is getting much more popular. Okay, based on the graph below, let's describe what happens with truck vehicle emissions as time moves forward. So there's a car graph, there's a truck graph, there's a both graph. I'd only like to look at the truck one just because it's a little more interesting right now. But generally speaking, if you look as you move time forward, as you go from 1975 up to well, I guess this graph doesn't quite go to 2020. Let's say it goes up to like 2017 or something. Generally speaking, over time, trucks are less polluting the more recent the model is, right? The newer car from like 2015 is less polluting than a car from 1980. But you may notice that in the late 1970s here, there's this weird spike. I don't know why that's there, but I just wanted to talk about trucks for that reason. It looks like trucks were, were getting more environmentally friendly, and then for a little while they were actually getting less environmentally friendly, or they were getting more polluting for a little while. And then there was this dip that started, mostly a dip that started happening. Okay, so this interpreting behavior from graphs is a very, very important skill. It's very important when looking at graphs in newspapers or in other classes that have quantitative things such as chemistry and biology. And I think the key point is to say that each axis represents a quantity, which should be labeled and should have units on it. And as you move along the x-axis, the kind of question you want to ask yourself is, does the y-coordinate, how does it change? How does the y value change? Does it increase or does it decrease? And use the thing to do really is to use a descriptive word based on the quantity that's for the y-axis to describe that increase or decrease. So as much as possible, yes, you should think, does y increase or decrease? But if you stop there, all you're doing is thinking in terms of math, and that's not enough. It's important to now connect that to the problem, to be very problem specific. So for example, in the cigarette smoking example, when the y value was decreasing, we didn't just stop there and say, oh, the y value is decreasing. That just sounds like math. That doesn't make much sense in that specific problem. It's more important to take that concept that the y value is decreasing and that y represented the percentage of teens that were smoking, to then convert that to the language of, oh, teen smoking is getting less popular. So that less popular, since the y-axis was about popularity, and the y-coordinate was decreasing, the y value is decreasing, we use this language like less popular. So interactive question. Suppose that the graph below shows how a metal object's temperature, let's say temperatures on the y-axis, changes based on its distance, that's the x-axis, from a factory. Then which sentence down below would accurately describe the relationship between the temperature of the object and the distance of the object? So is it A, the object gets hotter as it moves away from the factory, or B, the object gets colder as it moves away from the factory, or C, the object maintains its temperature as it moves away from the factory, or D, as the object moves closer to the factory, the object rises, or E, as an object moves closer to the factory, the object falls.